Hello and welcome to Dr. T's Math. In this video I'm going to demonstrate some statistical measures of central tendency using the TI-84 and show that it's a lot faster and more reliable than doing it by hand. However, doing it by hand is also an option. I just don't really recommend it so much anymore. So imagine we got some test scores here, and test scores are like 91, 93, 94, 99, 82, 85, 82 again, 88, and so on. So I got a stem and leaf plot here, and that shows us all our test scores, or some data. Since I'm a teacher, I think test scores are relevant. And we want to figure out, well, what's the mean, median, and mode in order to try to decide if this is like a reliable measure of student performance or something like that. And we can already see that, there's nothing down here, which is good, that students shouldn't be getting 30s and 20s and 10s and things like that. We can already see that there are a whole lot more A's and B's than there are C's and D's and F's, but that's also good, it doesn't necessarily mean it's bad. So in order to find the mean, that's this x bar here, also known as mu, what we're going to do is take the sum of all of the elements there from the first element to the last one, and that's what our xi is, and then divide it by the number of elements. And so the long way about going about this is to just list them all out: 47, 48, 52, 65, 74, oops, sorry, I already forgot one, that's why calculators are more reliable. 67, 74, 77, 82, 82, 85, 88, 91, 93, 94, 99, and then we're going to add all those up. Now, again, using a calculator since elementary school has made light work of arithmetic, and that's probably a good thing because, again, it reduces the overall chance of error. And so going over here to the calculator, I'm just going to go ahead and type these in. Now I've got two extra columns over on the left because I'm in landscape mode here. But this is in fact just exactly like a TI-84. If we look at the rightmost column from y equals up top all the way over to graph, same thing, and then because I'm in landscape mode on the iPad, then we get a little extra. So 47 plus 48 plus 52 plus 65 plus 67 plus 74 plus 77 plus 82 plus 82 plus 85 plus 88 plus 91 plus 93 plus 94 plus 99. And we get 1144. Divide that by 15. There are 15 elements in that set of scores, and we get 76.266. 76, so our mu is 76.26 repeating. And then we're going to use that in order to find the standard deviation. The standard deviation is going to be the square root of the variance, and this is the one that takes a really long time to do by hand. Some teachers will make you do it just as an exercise in good faith towards the mathematics. And what this all means is we're going to take the square root, it's going to be a huge square root, and we're going to sum together. It's going to be the difference from mean squared, or mean difference squared. So we're going to take our first number 47 and subtract from that, that's 76.26. And we're going to square it and then add that to the next number, 48 minus 76.26. Square it, and then I'm just going to give it a little dot, dot, dot. At the end, it's going to be 99 minus 76.26 quantity squared. And you can see that at the beginning, these numbers are going to be negative, but squaring it will make it positive, and at the end, these numbers will be positive, but we square it, and it's going to be positive still. Divide that all by n. This is a population. This is all the test scores in a group. Now, there's always a little bit of question of, on like a test or whatever, should you do the population or the sample mean? The sample standard deviation is going to be like n minus 1. but in this case we have every test score in the group, so it is a population. And so back on our calculator, I'm going to store this STO, it's right next to the 1, store that to alpha A, and enter. And the reason I do that is because there's so many decimals that I don't want to mess up here. And so just start entering it in, just like it was, 47 minus A squared plus 48 minus A squared plus 52 minus A squared plus 65 minus A squared plus 67 minus A squared plus 74 minus A squared plus 77 minus A squared plus 82 minus A squared. Oops. See, and this is the risk in doing it all by hand. There's an even easier way to use a calculator here. The calculator definitely reduces the risk of error, which when dealing with large numbers of data, or even just anything anymore, then the more accurate, more reliable we can be, the better, and the more efficient we can be with our time, the better. But you can imagine also some math teachers and some situations require us to work all these things out. And then also, it's always good to know that there's a formula behind the computer doing it for you. That doesn't necessarily increase comprehension of the whole topic, but it certainly helps to kind of think in procedural manner, right? Knowing that the computer is doing all of these calculations very quickly, and so here's our last number, 99 minus A squared, and that gives us 61,044. And now I need to take a square root of that, so I'm going second, x squared for the square root, and I'm going to go second, answer. Oops, sorry, nope. One step ahead. First thing I got to do is go answer. I'm going to divide that by 15. Divided by 15. And I get 271. Now I can take the square root of that, second, negative, enter. And we're at 16.474. So again, order of operations, doing everything inside the root sign first, divided by n, and we got our sigma is 4741. Now we can already see that there's going to be a skewness to this, and so we won't be able to do stuff like cumulative density functions or cumulative probability functions, but what I really want to do is take a look at a faster way to do that. So I've already entered in our list. This is our scores, 47, 48, 52, all the way. You can see that this is NL1 here, 15 equals 99. So we're all set to go. I'm going to quit out and then go back to stat. And I want to go to statistics. Nope. Go to calc. And we want one variable statistics because there's only one column. So I got one variable stats, and then I'm going to say second L1. Second L1 is behind the number 1. Press enter, and it gives us all those up front. And so we can say 2/15 times the square root of 15,266 is the same as we got here for sigma x. 2/15 times the square root of 15,266. And it's giving us other stuff like the minimum, the first quartile, the median, the third quartile, and the maximum. So let's exit out, exit, and then go back to this sheet here. Give myself some space. So we found by hand the long way the mean and the standard deviation. Standard deviation is the square root of the variance. Variance is hardly ever used, but indeed sigma squared is the variance. So now let's make ourselves that list again, 47, 48, 52, 65, 67, 74. I want to get it all in one row here. 82, 82, 85, 88, and am I going to fit it? Probably not. 91, 93, 94, just barely 99, barely. And we got 15, so let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Missed one. Which one is it? So we got 47, 48, 52, 65, 67, 74, and then right here we got to add in a 77. 77 right there. Okay, so now we got 15. And what we're going to do is split these up into quartiles. I know it's kind of a messy looking list because my handwriting's a little bit messy, but it doesn't require the best handwriting to make up the quartiles, so we're just going to count the middle. If we've got 15, then 8 is the middle. We're going to have 7 on one side. We're going to have 7 on the other side, 7 and 7, 7 and 7. And then the 8th one is in the middle right there. It's going to be our median. So let's count 1, 2, 3, 4, 5, 6, 7, and then 8th is our median. There it is. And then we're going to do the same thing again. Now we're going to have 3 on one side, 3 on the other, and we're going to find our median of the first half. That's going to be our first quartile, Q1. So 1, 2, 3, 4, there's our first quartile. I'm going to do the second thing for the top half for our third quartile, give them 3 on one side, 3 on the other. 1, 2, 3, 4, so 91. And then we can make ourselves a nice box whiskers plot like this, where we have our median, also known as quartile 2, Q2, and then we got Q1, Q3, and our minimum and our maximum. Our IQR then is equal to Q3 minus Q1, which is 91 minus 65. 91 minus 65 is what? 85 gives us 20, it's going to be 26. And so if we wanted to find outliers this method, then we're going to subtract 26 from 65, and we'll get 41 out here. That's going to be an outlier. And we're going to add 26, or I think it might be 1.5 times, sorry, 1.5 times the IQR. So we don't have any outliers on either end of the scale. Let's go back to the calculator. So Q1, indeed 65, Q3, 91. So that gave us all this stuff right up in one long list, and it's way faster. Can we find IQR on here? IQR, IQR. I don't see any IQR, but let's look at skewness. Skewness of list number 1, so second one, and it tells us that we are indeed skewed to the left. We have a left skew or a negative skew, if you're unfamiliar or don't remember what a skew is. This is going to be a right skew. A right skew is going to be like that thin taper, and then the left skew is over here, and that's exactly what we're looking at. We have more A's and B's than we do F's and D's, or C would be right in the middle. And so we have ourselves a left skew. Now that means we cannot find stuff like probability density functions and cumulative density stuff with, if we press second, VARs, then we got normal PDF up top and normal CDF secondly. We can't do any of this stuff without normal distribution. And so let's just imagine another data set that has normal distribution. So then we can do a probability density function. Remember, your empirical rule says that when you're looking at the median, 50% of the data are to the right of the median, 50% are to the left. And so then the probability of a piece of a datum being higher or lower than the median is 50-50. And then we have, here are our standard deviations. Plus 1 is 34%, and then another 13.5 for the plus 2, 2.35, and then outlier is going to be 0.15 on the right and also on the left. And then since it's normally distributed, this is symmetrical, where 68% of the data is 34 plus 34. That's within 1 standard deviation of the mean. 95% of the data, that's 68 plus 27, is within 2 standard deviations, and then 99.7% of the data are within 3 standard deviations. And this is where 6 sigma comes in. We have 1, 2, 3, 4, 5, 6 sigmas within 3 standard deviations of the mean. And then that is not including the outliers. So if you want 6 sigma certification, then you're going to have fewer outliers or no outliers, hopefully, in your production of whatever widgets or things that you're producing, or whatever services you're producing. But let's get back to the example where we're going to do a normal CDF function, a cumulative density function. So we've got a normally distributed set of data where the mean, median, and mode are all the same, and that's going to be at 80. And we know that the standard deviation is, it's a mu, standard deviation is 6.5, and we want to know what's the probability of some random piece of data, or some test score, in this case it probably looks like a test score, being less than 72. And so first we need to know a z-score. Z is going to be equal to the datum that we're interested in minus the mean divided by the standard deviation, and so that's going to be 72 minus 80 over 6.5, and you can see that 72 is going to lie somewhere in here. No, it's not going to be there. It's going to be somewhere over here, because 80 minus 6.5 is going to be 70. Well, it's 73.5, so it's going to be negative 1 point something, and we'll figure that out in a moment. We're going to have negative 8 divided by 6.5. Back to the calculator. So we're going to be using it just for simple arithmetic anyway. Negative 8 divided by 6.5 is equal to negative 1.230. So that's going to be our standard deviation. We're 1.230, 1.231 standard deviations to the left of the mean. Now let's go to second VAERS, and we're going to do a probability cumulative density function. Normal CDF, and then our lower bound is going to be negative 1 e, to find e equals second, comma, e99, so that's like negative infinity basically. And then we put a comma. Our upper bound is going to be 72, so from negative infinity to 72, you can't just put 0 for whatever reason. Now we're inferring that, test scores maybe are started at 0, but for data it could be up to negative infinity. Negative numbers are a possibility. Then our mean is 80 and our standard deviation is 6.5, and we get 10.9%. 10.9% of, there's a 10.9% chance of datum falling less than 1.23, and that makes sense given our empirical rule, because, well, there's only, what's 50 minus 34 is equal to 16. There's only a 16% chance of something being right at that cusp of the first and second standard deviation to the left of the mean. And so we're into that second deviation to the left of the mean, and so there's going to be a less than 16% chance, and indeed it's falling kind of exponentially here. And so it makes sense that 10.9% is going to be somewhere in there. Okay. If we were going to do it the old-fashioned way, we would have had to look at one of these tables, right? And a long time ago, people spent their whole lives just calculating numbers, and so luckily, we didn't have to do things again and again and again. And so what were we at? Negative 1.23. Negative 1.23, looking at the table, so we're going to go down to negative 1.2 and then arrow over to 3, and indeed right there it is, 0.1093. And so in this case, the normal CDF is maybe just a little bit faster, but we had to calculate the z-score, or we didn't actually, indeed. We didn't have to calculate the z-score, sorry. In order to use the calculator, we had to calculate the z-score, so it was an extra step to use the table. So the calculator is both faster and it's more efficient, which is definitely desirable when looking at a standardized test or something like that. Okay, thank you. This has been Dr. T's Math. Thanks for watching.